Hi, welcome to videos on control system. So in this video we'll see the compensation. The topic of this particular video is lead compensation. Let us first have a look at what is the need of compensation. So it is used to get the desired steady state error by adjusting the steady state static error coefficients, and it is designed to get the required overshoot and the settling time. So that can be done by adjusting the desired transient parameters, and it is used to get the desired gain and phase margin by adjusting the margins of the system. Of course, it should be made immune to noise at higher frequencies. This is how an uncompensated network will look like with negative feedback. So with this uncompensated network, we'll actually find out what is the gain required to get the required error coefficient so that your steady state error is as small as possible. And then we estimate the GM and PM. If the gain and gain margin, phase margin is not sufficient, we'll go for compensation of the network, compensation of the system. So before we actually move on to the compensation of the control system, we try to understand what is the frequency response of a system indicate. At low frequency, it actually indicates the steady state behavior of the closed loop system. So at mid frequencies, it actually shows what the relative stability of the system. At higher frequencies, we'll get to know what is the complexity of the system, that is how good it is immune to noise. So requirements of an open loop system should be to have a better system. So we are supposed to have a large gain at low frequencies, and at close to the cutoff the gain crossover frequency, we have to have a slope of almost minus 20 dB per decade to have a better phase margin, and it should have a larger slope at higher frequencies to minimize the effect of noise. So these are the requirements, and error coefficient should be as high as possible so that we will get the steady state error small for a given closed loop system. So this is a compensated system. So you can see this was GC, G, the uncompensated. This is a compensation network. So this is a lead compensation. Since it's a lead compensation, we need to have the zero first and then the pole in the transfer function of this compensator. So that's what is this we have. So you can see there is a 0 at 1 over t, and there is a pole at 1 over alpha t. So since this should be far away, so alpha should be always between 0 and 1. So by we can check the error coefficient of this and then adjust the gain and phase margin, adjust the poles and zeros to get the desired GM and PM. So what we'll do here is we'll take up an example and try to find out, okay, how do we compensate this system. So the system has got a gain of open loop gain of 4, and it has got poles at origin and at -2 on the S plane. It is designed to have the velocity error coefficient of around 20, and the phase margin should be at least 50 degrees and the gain margin should be at least 10. So we thought, okay, we can actually see what is the open loop the kV of this system without compensation. The kV of this system, that is the static error velocity error coefficient of this particular system without compensation is almost 2 second inverse, and then phase margin is actually 51 degrees and gain margin is infinite. Since we don't have the desired kV, that is the static velocity error constant, we are supposed to provide a compensation for this system. Since kV is 2, it will going to have a lot of error. The steady state error will be more here. So even though phase margin is close to the desired one, the gain margin is too high. Since this has got a lot of steady state error, so this need to be compensated using a lead network, a lead compensator. So that's what we are doing now. So in order to increase the value of kV to 20, so that's what is this 20. So we are adding a constant term k. So we are actually finding what should be the value of k so that we'll get a better kV, that is of 20. To have a kV of 20, so this GFI should be multiplied by 10 times so that we're going to get the desired value of kV, because we are looking for a kV of 20. So whatever 4 by s into s plus 2 we had, so that should be made 40 divided by s into s plus 2. so that this should be multiplied by 10 now. If this is multiplied by 10, so naturally we're going to have an increased value of kV. But if we simply increase the value of this 4 to 40, naturally the phase margin will reduce, and then the gain margin will also, let us see what happens to gain and phase margin. So by simply introducing this K and without doing that compensation network, the GM is still infinity, but the PM has become 17 degrees, which is very poor here. So now, but the PM required is around 50 degrees. So even though we might have achieved the value of velocity error coefficient of 20 second inverse, 20 per second, so we're not getting the desired phase margin, even though the gain margin is also close to infinity. So we are supposed to add another phase margin of 33 degrees through the compensation network. So since the addition of this K has actually moved this phase margin, gain crossover frequency to a larger value, so now we need to introduce a phase of almost 33 degrees. So that is by using this GC, that is the compensation network. But you can see this is that compensation network, this is that K times G. So note that any addition of any network will certainly push your gain crossover frequency to right side. So when the gain crossover frequency moves to right side, naturally it is going to reduce the phase margin. So since the phase margin is reduced due to the introduction of this compensation network, so we are not supposed to only compensate 33 degree, so which was supposed to make that 17 to 50. So let us introduce another extra 5 degrees for compensating the movement of the gain crossover frequency because of introduction of this GC. So naturally what we are trying to do is, now at a particular frequency which corresponds to omega GC, we are supposed to have introduction of 38 degree by this compensation network, so that we can have 38 degree minus of this 5, which is due to the movement of the gain crossover frequency, and the existing phase margin was already 17 degrees, so it comes out to close to 50 degree phase margin. So we are actually trying to find out what is the desired phi m. The desired phase shift should be 38 degree. So with this 38 degree, we can actually find out the alpha value, which is one of the design parameter here. So the value of this is the actual compensation network. You can see this is the value of alpha we are looking at, and this is the overall transfer function of the system after doing the compensation. This is at the maximum phase shift we're going to have at a particular frequency, and you can see this is for the desired phi m is equal to 38 degrees. The corresponding value of alpha will be 0.24. So the corner frequencies of the 0 and pole happens to be at 1 over t, and this is again omega, this is omega z, this is omega p. Let me slightly change this. This is the 0 frequency and this is the pole frequency, and we know that the maximum at a frequency which is the geometric mean of the two corner frequencies exactly, which is ODR phi m, and we can actually find out the amount, because when we actually introduce this particular lead network, it will certainly change some magnitude of your Bode plot. So we'll see what is the effect of this by looking at the Bode plot. You can see this is when we actually introduce this phase lead network. When we actually introduce the phase lead network, so there is a reduction of gain by minus 6.2 dBs. So at a frequency at a frequency equal to 9 radian per second. So we know that since it has reduced the gain by 6.2 dB has been reduced, so this we need to compensate here. So now because this is reduced by 6.2 dB, the omega GC comes out to be 9 radian per second. That's exactly what we have here. So this was the earlier plot. So this was actually omega GC, which was happening at almost close to this particular frequency. Since we introduced this phase lead block, that has introduced a negative gain of minus 6.2 dB. So your omega GC has changed to 9 radian per second. So at this 9 radian per second, I have to have a phase of 38 degrees. So keeping that in view, so we have actually calculated so this omega C, which happens to be 9 radian per second, and alpha value we found out to be 0.24. The 0 and pole frequencies are at 4.41 radian per second and 18.4 radian per second. So if we keep the pole at 18.4 and 0 at 4.41 radian per second, we'll certainly get a phase, positive phase of 38 degrees at 9 radian per second, which is what is required. So we're going to end up with the transfer function of the compensation network as given by this, and it's this is the pole 0 form, this is the time constant form. So what we're trying to do here is we'll divide this GC by k times and multiply by G1, where G1 is actually G times G of S into K. So that's what is this, K is equal to actually 10. So this is GC by 10 and this is 10 into G. This 10 and 10 will cancel, we'll end up with GC into G. So this is the compensation transfer function. This is the real system transfer function. Now what we'll actually plot is we'll actually plot the Bode plot for GC by 10 and 10 into G, which will going to give the product of these two will going to give the compensation of the entire network in terms of phase lead compensation. You can see this is the magnitude plot. If you can see this corresponds to the dotted line starting from here corresponds to G1, which is 10 into G, and you can see this is the phase lead compensation network. This is of 0 dB per decade till 4, and at around 18.4 there is a pole here. So there is a 0 at 4.4, there is a pole at 18.4, and this is plotted with GC by 10. So we know that this is individual plots, and this happens to be the complete plot, that is the product of GC and G. So if we can carefully look at this, now it has modified because of the introduction of this lead network. Here you can make out the change in the phase plot. So this was the earlier phase plot. The phase plot has now changed because of the product of G and GC. If you can carefully notice this here, so this is omega GC. So at this omega GC, which is close to 9 radian per second, so we have a phase margin of almost 50 degrees. The corresponding gain margin at so we still have a gain margin of almost infinity, because we expected a gain margin of almost minimum 10 dB. So we have a gain margin of infinite, but we have a very good phase margin of 50 degree, even with having a very good value of kV, which is 20 second inverse. So this way we can able to get the desired design using compensation. And you can see this is the effect of compensation on the time response. The uncompensated response has got slightly increased rise time. Now that has been reduced. So this will going to have a slight overshoot over here, because you can see now as the rise time reduces, the overshoot is slightly increased. So this is one disadvantage of this phase lead network. But anyhow, we're going to have this. You can see this is settling sooner. So that's why since the kV value of this is more, the steady state error is less in case of compensated network. So we'll see next the lag compensation. So how do we compensate network using lag network?